Greetings, everyone. Now it's time to finish up our solving techniques, or maybe it's not finishing up, maybe it's still starting. I don't know where you're at in the videos, but it's time to continue on here, I guess is a better way to say it, with some other just random pieces of solving that come up here and there, some little tricks. I hate to use that word. I know some of you out there watching probably feel the same. Other methods that will avail themselves to you whenever we're going through some of our college algebra. Okay, so these methods are just some other things that we haven't hit yet, but are important in your solving techniques to just kind of have out there and practice. Okay, so the first grouping here is some other factoring methods that will come up in solving. Okay, and typically with factoring you'll find that really what we're doing is we're just solving polynomial equations, things with whole number positive powers, and you've probably done quite a bit of the quadratic type of factoring. These are going to be ones that kind of look like that and sometimes don't, but still the same idea of factoring and solving. Okay, so let's start with m to the fourth minus 14m plus 45 equals 0. So remember, paramount with factoring, first thing you always want to have is that equals 0, right? Step one, got it, done. All right, so now we just want to factor this. Whoops, this should have been a squared, right? First thing you should notice is that it looks just like a quadratic, right? It does. It has this thing where the 4 is twice as big as the 2, or 2 plus 2 is 4, really is the way you should be looking at it. And I want to factor this out, okay? So think of it kind of like I have something that looks like this. X squared minus 14x plus 45. Think of it like this. And I want to factor this thing out, right? I would look at it as what two numbers multiply to 45 that add to negative 14. Well, that would be x minus 9 times x minus 5. Okay? This is no different. I just have to make sure that the things that I'm factoring this out into still multiply to give me the m to the fourth and the m squared. Well, that's easy enough. I'll just put m squared in the front of each one of these, because m squared times m squared will still, the exponents will add up because you're multiplying, right? And then the cross terms will each have an m squared, which will still give me the middle term. And it works the same as this guy over here, minus 9 minus 5. Great. So the m squared minus 9 is a difference of squares. I can factor that further. M squared minus 5 technically is not a difference of squares. You could try to argue it, but we typically don't. So I'm just going to leave it as is, and I can still solve it. Okay? Now, let me get this out of the way, and let's just solve the one on hand here. Remember, once you get to this point, you've got it equal to 0, and you've got objects that are multiplied. You can split them up and solve them. Okay? So here, this one's going to give you m equals 3, right? This one's going to give you m equals negative 3. But then let's talk about this one a little more. I'm splitting them up, and each one can be equal to 0. So what I'm getting is that m squared minus 5 can also be equal to 0 here. Okay, well, I'll just add the 5 over, like so. And then to get rid of the squared, I'll go ahead and introduce a square root. But remember, if you bring a radical to the party, he brings his buddies to crash the party, right? Because I brought the radical, he brings the buddies, okay? And his buddies are plus and minus. So m equals plus or minus square root of 5 in this case, which I can't simplify that without plugging it into a calculator. I want you to notice that this is actually 2 answers, and then here's 2 more, right? For a grand total in that case of 4 answers. And that should mean something to you. We started with a fourth power. Okay? In a polynomial equation, that highest exponent is going to tell you the maximum number of answers that you can have, and the amount that you would typically want to expect to have. Okay? The only reason that you would have less than 4 total answers is if one of them repeats, and we call that multiplicity, right? Like if I had gotten 3 and then 3 again, right? That would be the only way I'd get less than 4 answers, because one of them's repeating. If none of them repeat, you'll have 4 answers, okay? So there's the 4 answers for this one. All done mostly through factoring, right, that you're already familiar with. Next one, y cubed minus 2y squared equals 25y minus 50. Okay, so again, we're going to approach this by factoring. And the big red flag for this that I'm noticing is, the fact that it is a polynomial, the highest is a cube, and it has 4 terms. When I'm thinking 4 terms in factoring, I'm thinking it could probably be grouped. And you can always double check, right? 1 and 2, 1 is half of 2, 25 is half of 50. It seems to line up, right, with the signs and everything. Okay? But remember, step 1 in solving by factoring is getting something equal to 0. So what am I going to do? I'm going to subtract 25y and I'm going to add 50 to both sides to get rid of those, right? Okay, so what does this land me with? I've got the equals 0, I know. I've got my y cubed still. I've got my 2y squared still. But now I've got minus 25y and plus 50. Okay? I've got 4 terms here, which means I can attempt to factor by grouping. Okay, so grouping is when I can take it into 2 groups here, and I can find a common factor in each one. Okay? There's no GCF from all of them, but I can find a common factor here and a common factor here, and then hopefully whatever's left over is common between the 2 groups for me to finish it. Let's take a look. From these front 2 guys here, I can take a y squared, leaving me with y minus 2. Double check. Y squared times y is y cubed. Y squared times negative 2 is negative 2y squared. Absolutely. Whenever you're factoring by grouping, the second group needs to always match this middle sign here. That's a good way to remember what you should be factoring here, okay? So I'm definitely factoring a negative out of both, okay? So I know that I'm going to be having something like this in my setup, right? Because a negative times a negative is going to give me this positive, and a negative times whatever this positive is going to stay negative. Okay, now look at the numbers, 25 and 50. They each have a 25 that I can factor out. That's going to leave me with a y, and 50 divided by negative 25 is negative 2. Look, I got exactly what I wanted. The leftovers are the same. So what I do is I pull that out. I pull out a y minus 2, and I'm left with y squared minus 25. Like that. That's a difference of squares. So I've got y minus 5 times y plus 5 times y minus 2. And look, each one is linear now, and they're all multiplied, and it's equal to 0, which means I can split it up. So what 3 answers did I just get? I got y is equal to 5, negative 5, and positive 2. Again, notice it's 3 answers, and I started with a y cubed. Okay? All right, so one more example of factoring here, a little bit more obscure, and that is it's just not seen as much because people try to take the easy road on this one. Now, if you look at it, it's obviously polynomial like the other ones. It's got x to a positive whole number power, right? And it's cubed, so I should have 3 answers, right? If you go at it directly and say, oh, let me just take the cube root of both sides, right? If you try that first, cube root like this, without some really extensive studying and some of the understanding of the larger generalizations of our number system, you may not realize that a cube root always results in 3 answers, and those answers are based off of the complex number system. Sometimes they're imaginary, sometimes they're all real, but without some of that extensive experience, you may not realize that this directly would give you 3 answers, or even how to go about getting that. Instead, a problem like this, we should use factoring at this time to really see where are those 3 answers coming from. Okay? Now I know what you're thinking. There's not much to factor here. But there is, though. There really is. There's a lot of factoring here, and it looks just like one of those methods that you should have seen. Like always, factoring starts with an equals 0. So I'm going to subtract 8. Then if you look really closely, you'll notice that what this is a difference of 2 cubes. Because 8 is 2 cubed. Now, of course, 8's a special number, right? So you're saying, well, couldn't I do this with any number? Sure. If you're willing to write things in terms of radicals, you can still do this. Okay? I'm just using an example of something that we can see more clearly at this beginning stage. Okay? However, the factoring method is the same, no matter which way you look at it. The difference of cubes, a cubed minus b cubed, is equal to a minus b times a squared plus ab plus b squared. That's one of our factoring methods, is the difference of 2 cubes. And I've got that here because 8 is 2 cubed. So for that format, x is my a and 2 is my b. So if I factor this by cubes, difference of cubes, I'll have x minus 2 times x squared plus 2x plus 4. Because that'll be a squared is x squared, a times b is x times 2, and b squared is 2 times 2. And it's still equal to 0. All right. So remember, when things are multiplied and equal to 0 here, that's when I can start splitting. And this one immediately is going to give me that answer that we expected before. If you had gone the direct route with the cube root, 2 is the answer that you would have gotten. So it seems like a lot of extra steps just to get that, right? But that's not why we did it. This answer is the easy one. You still have this chunk that's also multiplied and equal to 0, and it's sitting there waiting. That's where the other 2 are coming from. That's that leftover bit. And look, it's a quadratic. So even if I can't factor this next piece, I can definitely solve it. We've already talked about the quadratic formula. And that's exactly what we need to do here. Because the first thing you should notice is that this is not factorable. You should expect that from a sum or difference of cubes. The leftover bit, you should never expect to be factorable. Because if it was, then we'd have more to our factoring formula, right? Okay, look. It's a quadratic. It's already equal to 0 too. It's in a squared plus bx plus c format. I'm going to go straight to quadratic formula. X equals negative b plus or minus square root b squared minus 4ac all over 2a. Right? Okay. So right here in my radical, I've got 2 squared, which is 4, minus 4 times 4, which is 16. Okay, do you see it yet? 4 minus 16 is going to give me a negative number. And this is why some of these answers might seem a little bit more obscure, because I'm doing a square root of a negative number, which leads to imaginary and complex, right? Okay, so here it is. I need to simplify this radical, the square root of negative 12. The square root of negative 12, I can split up into square root of 4, square root of -1, and square root of 3, right? 4 times -1 times 3 is -12. The reason why I put these two in the front is because those are the two I can actually simplify. That's 2i and square root of 3. Alrighty. So let's finish up our solution here. Or solutions, plural. X is equal to -2 plus or minus, the simplification there is now 2i square root of 3 all over 2, right? Don't forget, when you have something that will work out with both fractions, though, you see I can actually do 2 over 2 and 2 over 2. I'm going to go ahead and split this up like this. I'm going to take the denominator and distribute it to each piece of the numerator over the addition and subtraction. That's just distributive property. That's okay. So then I get x equals -1 plus or minus I square root of 3. This is two answers right here, two complex answers. Notice they are conjugates. Whenever you have something that's going to be imaginary or complex, and we did not start with imaginary or complex numbers, they're always going to come out with conjugate pairs like that. Okay? So I've got three answers. I've got my 2, I've got -1 plus I square root of 3, and -1 minus I square root of 3. That's those three answers. If I take them and cube them again, right, I will get 8 as an answer. This next type I want to talk about are the rational exponent equations. And technically these are part of the radical equation solving method, but this is when they start getting all mixed up with the exponents and you have the whole conversion thing going on. And rational exponents sort of just get kind of set to the side here. And you can still work them, you know, the same way. Okay? So this is what happens, is a rational exponent really is something with both a radical and a power, right, at the same time. I always call it power over root, or the root is in the bottom of the power because it's like a tree, right? The root's in the bottom. So in any case, what you've got is two things going on. But if you leave it in rational exponent form, you can take advantage of some exponent properties that allow you to sort of solve it pretty quickly. Okay? Especially if you're able to get through some rational exponents, you know, within one calculation. And if these end up being something really messy, they're very easy to plug into the calculator too to get that decimal approximation if you absolutely had to. So let's look at this. Don't forget a couple of things. One, when I'm solving these, my end goal is to have x to the 1 power. Right? This is my goal, to have x to the 1 power. Okay? And then I've also got that old exponent property that if I have something raised to a power, and then I raise that to another power, like q, let's say, then that's the same thing as multiplying the two powers, p times q. Okay? So right here, I can actually use that to my advantage. I'm going to raise this to some power, and then that's going to cause the two exponents to multiply. So if I can think of something that when I multiply by 4/3, I get 1, then that's the power I'd want to use, right? Well, that's the lovely thing about fractions. You can always multiply them to get 1 with their reciprocal. So here's what I'm going to do. I'm going to raise both sides to the reciprocal exponent. Okay? Now be careful. Sometimes you get a little muddled here. I am not multiplying by 3/4. I am raising it to a 3/4 exponent. It's a power. Okay? However, since these are both exponents and one is acting on the other, they do multiply the numbers. But I'm not actually doing multiplication here. Okay? So here my power becomes 12 over 12, which is 1, which is exactly what I wanted. So now I just need to be able to perform 16 to the 3/4 power, right? Well, don't forget, that's just the fourth root of 16 to the third. The fourth root of 16 is 2 to the third power is 8. Be extra careful though. This is an even powered root. And those are the ones that bring the plus and minus with them. So here, theoretically, technically, I have to put plus and minus 16 to the 3/4. If it had been an odd root, I wouldn't have to do that. But I'm getting plus or minus 8 because it's 2 to the third power, right? The fourth root of 16 is 2 to the third power is then 8. Okay? Can I do the same thing with a negative exponent? Absolutely. Again, I would raise both sides to a power that when multiplied by the current exponent would give me 1. That would be negative 3 over 2, right? Those are reciprocals. So over here, same thing, the negative 3 over 2 power. Okay? So I just need to remember some of my rules of exponents here. A negative exponent moves something into a denominator. And then again, pay attention to that root number here on the bottom. That is a 2 root that I'm performing. Well, that's an even powered root. So again, I got to bring out that plus and minus just because it's an even root. Okay, so the square root of 16 is 4 to the 3 power is then 64. So I'm getting y is equal to plus or minus 1 over 64. Okay? So that's how I handle rational exponents once I get to that step. Let's step it up a notch to this other example and actually go through and solve it here. Okay? So I'm going to solve for z, but first I need to start, peeling off the pieces of the package here. First, the 2 is outside of the parentheses and is not being acted on by the exponent, right? So the 2's got to go first to get him out of the way. I am going to start by dividing by 2. Divide by 2, divide by 2. Okay, so I have z plus 7 to the 3/2 is equal to 64. All right. From there, I want to get rid of the exponent so that I can drop the parentheses. That means I need to raise a power on both sides that will multiply with 3/2 to give me 1. Again, I'm not multiplying. I am using exponents here. The 2/3 exponent on both sides. These exponents do multiply, but I am not actually doing the action of multiplying here. Okay, so I have 6 over 6 power, which is a 1 power. So this is good to go. This is just z plus 7. Then 64 to the 2/3. What you have is the third root of 64, which is 4, squared is 16. Now, why didn't I put the plus or minus this time like I did over here when I did my power? Again, that was an even root. The 2 was the root here. The 4 is an even root. It's the root. Here I'm doing a third root. It's an odd root. No plus or minus necessary. Last step, subtract the 7. So I'm getting that z is 9. Okay? The third extra category for solving here we call quadratic type, because they're not exactly quadratic, but they do fit the same exact structure as a quadratic as far as all of the way the pieces work together. We've actually already solved one like this before. We solved this one earlier with factoring, but now I want to emphasize a different approach here because not all quadratic types might be factorable. Okay? It fits the bill of quadratic type if it looks like a quadratic. Okay, now let me get more descriptive than that, right? You can't just, oh, you look like a quadratic, right? No, look, what I'm going to do here is you're going to look at it. It still has the 3 terms, right? The a, the b, and the c terms equal to 0, okay? And the power is double the higher term than it is the middle term, okay? That's how you can tell something is that quadratic type. Anytime this power is double of that power. So it could be, 4 and 2, it could be 10 and 5, whatever you can imagine, right? 1 and 1/2 would also work, okay? As long as those two exponents have that relationship and you've just got your three terms, you're staring at a quadratic type, okay? Which means I can still solve it like a quadratic. So like we did earlier, right? We factored it like we do some quadratics. Let's go the other way though, like I said, and let's use the quadratic formula now to solve it. We're going to do it on the one we've already seen so that you can see the answers come out the same. And then I want to show you one that's a bit half a step up. Okay? So I can see it's a quadratic type. Let's apply the quadratic formula. Well, remember with the quadratic formula, usually the x is right here in the middle, right? And that's technically the thing you're solving for. The x, right? The thing in the middle. So this piece right here, whatever the middle term is, this guy, is the one that you're actually solving in your quadratic formula, okay? So instead of x equals, you look at whatever this middle term is. That's your x. Okay, so here I'm going to say m squared equals. And then I'm going to use the formula. There shouldn't be any other letters in there. A is a number, B is a number, C is a number, right? A is 1, B is -14, C is 45. So let's do that. I've got -14 plus or minus square root -14 squared minus 4. A is 1, C is 45. All over 2a. Okay? So let's go ahead and start writing out our next step. M squared is equal to -14 is 14 plus or minus square root of 14 squared is 196 minus 4 times 45 is 180 all over 2. Alrighty, so I've got 14 plus or minus the square root of 16 all over 2. Yay, square root of 16, right? Yes. So again, I've got m squared is equal to, and I'm going to go ahead and split it up now because I know what the square root of 16 is, and I can do one for each of these because I've got more solving to do. I've got 14 plus the square root of 16, which is 4 over 2, or m squared is equal to 14 minus 4 over 2. Alrighty. Well, look, this is telling me that it's m squared is equal to 9, because that's 18 over 2. And this one is telling me it's m squared is equal to 5. Right? Well, this is an easy one. This is going to give me plus or minus 3, because I'll do the square root there. And don't forget, when I introduce the radical, right? Get the plus or minus. Same thing here. We solved this one directly earlier. That's plus or minus square root of 5. So as you can see, it's the same 4 answers. And I'm just solving it with the quadratic formula instead of factoring. Okay? If it's that quadratic type, you just got to remember the middle thing is your x, your object. Right? Middle thing, m squared. And then the numbers work exactly the same because it is a quadratic type of structure. Okay, so then let's look at this one over here. This one's a bit messier. It's not factorable, right? There are not two numbers that multiply to -7 that also add to 5. So this one's going to be quite messy because it's going to have all kinds of radicals flying over the place. But that's why we have the quadratic formula to make our work more efficient, more concise, and doable even, right? So let's go through it. I've already got the equals 0. I'm noticing that the 4 is double of 2, so it's a quadratic type for sure. And my object of interest is the x squared, right? There's my object of interest. All right, so x squared is equal to -b plus or minus square root b squared minus 4a, c is negative 7, all over 2a. Okay? So I've got negative 5 plus or minus square root 25 plus 28, all over 2. Okay, so we've got a total of 53 under the hood there. X squared is equal to negative 5 plus or minus the square root of 53 all over 2. And then, of course, at this point, you would just double check that you can't simplify it any more than we already have. Square root of 53 is not going anywhere, right? That's not something that's going to break up into anything useful. Okay, but I still haven't solved for x. X is still being squared, okay? Now I need you to realize something. We've already got 2 possibilities over here. And I'm about to square root again, right? To get rid of the squared on the x, which, since I'm introducing the square root, that brings the plus or minus with it, right? Because it's a square root. It's an even powered root, okay? So I need to be able to realize that I've got 4 different combinations that are about to happen. I'm going to be bringing up another plus and minus when there already is a plus or minus. So I can have plus plus, I can have plus minus, minus plus, and minus minus. Okay? Let's go ahead and do the step, and then let's write out the solutions here. Okay? So I'm going to take the square root of both sides. Okay? Yes, I know. Square root on a square root. Very yummy. So this is what I've got in a concise way of writing it. Plus or minus square root negative 5 plus or minus the square root of 53 all over 2. Okay? All right. So I'm going to have 4 answers there, as you can tell, because I can do different combinations with the pluses and the minuses. All right? If you have to write it in what we call exact form, this is about the best you're going to get, because I can't simplify any of the fractions or radicals inside, and I've got another radical on top of that now. Forget it. That's the exact form for any which way you want to write it. Okay? However, if you need the decimals and you're willing to do some number crunching, right, then we can definitely find the actual numbers that go there, whether they're real or imaginary, actually. Okay? So let's go through that. Let's write down the 4 combinations. X could equal the square root of negative 5 plus square root of 53 over 2. Or it could also equal the square root of negative 5 minus the square root of 53 over 2. Or the negative square root of negative 5 plus square root of 53 over 2. And lastly, the negative square root of negative 5 minus the square root of 53 over 2. Okay? Now, real quick, I'm going to need you to realize that the second and fourth possibilities are imaginary. Because notice, the numerator is going to be negative. The denominator is going to be positive, which is going to make the entire inside of this square root negative. This is the square root of a negative value. Okay? So this is going to be an imaginary number, and this is going to be the negative of that very same number. Okay? So fortunately, the same relationship, just not imaginary for the first and third. You'll notice it's the same inside, right? One's positive on the outside, one's negative on the outside. So I only actually need to crunch these two, and then those are just going to be the negatives of them, right? So that's pretty straightforward. Let's go ahead and crunch this first one. Okay, so negative 5 plus square root of 53, and then I'm going to divide by 2. Okay, now I'm getting 1.14 for just the inside portion. I'm going to hit square root of the answer, and I'm getting 1.0677. 335, and it's got some more garbage after that. Okay, so that's one answer right there. That means this one over here is just the negative of that, negative 1.0677335, da 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 da. Okay? Now, I also have these answers to worry about. So I'm going to go back, and I'm going to hit the minus there, divide by 2. The inside right here is negative 6.14. Inside. But that's the square root of a negative number. Okay? So the calculator can't handle that. I'm going to drop the negative. Okay? I just hit times negative 1, and it gave me 6.14005. Okay? I've got the positive now. I know that it's negative in there, which means I'm going to put an I on the answer. But I need to know the square root of this number, the value part of it. So square root of that, 2.4779. 2.4779. 13. That's good enough. I. That's important, right? It was an imaginary value. And then, of course, the one over here is just the negative. So negative 2.477913 I. Okay? And that's just if you have to have all of the actual answers maybe to plug in some sort of application. Okay? Most of the time when you're solving these things, they can tell you just to stop at the exact form, which would either be here or writing those out. Let's finish up this lecture with these last two examples that I want to throw at you, just so that you can see that it really does spread out to all different formats with this quadratic type. Okay? Now, of course, these may not come up that often, but I need to really drive home to you how this quadratic type is useful across many different structures. Okay? So notice, again, I've got a quadratic type because it's the three terms, right? With the bottom one being just a number, and then 2/3 is double of 1/3 in the exponent. So I can still treat this like a quadratic. And if it's factorable, I could try to go ahead and do that. But again, remember, if factoring doesn't appear to you right away, formula is always more efficient, saving time and quicker. Okay? And of course, saving time, yeah. Okay, so I notice it's a quadratic type. Important. It's already got the equal 0. Let's go for the formula. So which piece is the formula equal to? Don't forget. It's always that lower powered middle piece, this. That's where your x is in your quadratic. So I have a to the 1/3 equal to negative b plus or minus square root b squared minus 4, a is 5, c is negative 4, 2a. Okay? So that's negative 8 plus or minus, and then I've got the square root of, well, let's see real quick. This is 64 plus 20 times 4 is 80. Right? So that's the square root of 144. That's a nice one. Right? That's just 12. Okay, so I've got a to the 1/3 is equal to negative 8 plus 12 over 10, or a to the 1/3 is equal to negative 8 minus 12 over 10. All right? Okay. So right here I've got a to the 1/3 is equal to negative 8 plus 12 is 4 over 10. 4 over 10 is 2/5. Over here I have a to the 1/3 is equal to negative 20 over 10, which is just negative 2. One step left in each of these. Each of them is to a fraction power. You remember how we handled those? I have to raise it to a power of the reciprocal. So I'm going to raise it to the 3 over 1 power. But 3 over 1 is just 3. So I'm really just cubing both sides here. Same thing over here. I'm going to raise it to the 3 over 1 power because that's the reciprocal, which is really just cubing it, right? Okay, so my two answers for A are 2/5 cubed, which is 8 over 125, and here negative 2 cubed, which is just negative 8. Okay? All right, and then just a little bit more dramatic over here, even though it doesn't look as yucky with the powers. It looks weird with that structure in the middle, right? It makes you like, oh, I just want to FOIL this out and solve it. It's actually quicker if you don't do that. The first thing you should notice is that these two are the same base, and the 2 is double of 1, so it's still a quadratic type. Okay? But don't see the 5x plus 7. Don't see it. This is 3a squared minus 10. Same object, so just call it a again, right? Plus 8. Some people would even write it down with the a if it makes you feel more comfortable. Some people would actually just go ahead and write it. They call it substitution when you do this. And if it makes you more comfortable to solve it that way, fine. I prefer not to lose track of my 5x plus 7. And I'm going to solve it with the formula anyway. Okay? Where's my middle piece? My middle piece is this guy right here. Right? My A is 3, my B is negative 10, and my C is 8. Right? For my quadratic A, B, and C, I mean. Okay? So again, I'll have 5x plus 7 is equal to negative B plus or minus square root B squared minus 4ac and 2a. Right? Okay, so real quick, that square root has a 100 minus 12 times 8 is 96. Right? So that's a square root of 4. Negative 10 is 10, plus or minus square root of 4 is 2, and then all over 6, right? Okay, so here we go. I've got 5x plus 7 is equal to 10 plus 2 is 12 over 6, which is just 2. Or 5x plus 7 equals 10 minus 2 is 8 over 6. 8 over 6 is 4/3. Well, look, I've got two real quick linear equations that I can solve. This one's even faster than the other one. It's already just a whole number. If I just subtract 7, negative 5, divide by 5, I get x is negative 1, right? Got one answer. Okay. On this one, if you remember, if you prefer not to deal with fractions, then the way to get rid of it is to multiply. So here I'll just say times 3, times 3, times 3. That would give me 15x plus 21 is equal to 4. If I subtract the 21, then I have 15x is equal to negative 17. Divide both sides by 15. And I have negative 17 over 15. Okay? All right, guys, so I hope that this has helped you see that there are a few other varieties of equations out there that we do have to have methods for solving. And after you practice them a bunch, I hope this has helped you get through those methods easier.